How do you take the best of how we as a species know how to design hardware and apply it to every single design?
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. Today in the lobby, we're joined by Duncan Haldane, co-founder and CEO of Jidex. This is a tool that, when I heard about it, sounded too good to be true. This tool lets you avoid drafting schematics. You don't have to go in and draw the wires for a chip and then redraw everything when that chip goes out of stock. And then if you're like me, get a wire or a resistor value wrong somewhere and spend way too long debugging. With Jidex, you write some code to functionally describe what you want to do, and the tool helps sort out all the details. We'll get more into that because it sounds bonkers, but also amazing. We'll also talk robots because Duncan was a PhD research scientist at Berkeley and is a Guinness World Record holding roboticist. Duncan, thanks for being here today.
Excited to be here. Thanks for having me.
I'm curious, how did you get into science and technology?
I think I always just liked building things. I was building all sorts of stuff, little electronic things, a credit card reader, little audio amplifiers, and then in high school I started building robots and just seeing something that I could build that went out and moved matter around on the surface of the planet. That was pretty cool.
So what sort of robots were you building in high school? Because I understand there's a bigger story here, so this is just the tip of the iceberg.
Yeah, in high school we had kind of like a self-funded small robotics club that we put together, and we built this all-terrain robot. It was actually inspired by this cart that we had at the grocery store I worked at. It had one middle wheel bigger than the smaller, outer wheels, so it could go over curbs. I was oh, that's kind of a cool design. So we built a robot that way and also made it reversible, so you could throw it down a hill and it could land any side up and then start driving and go over bumps and stuff. Yeah, it was a lot of fun. Actually, it's made out of scavenged car parts mostly.
So it was made out of scavenged car parts. Did you just have cars lying around, or where did you scavenge these parts from? And what were people in your family and your other students thinking about these contraptions that you were building?
Yeah, so we went to an automotive pick yard. So it was just those businesses that kind of just have a big field of broken down cars, and you can go digging basically. Family is generally supportive. I think they're just glad we put down some of the more chemical fire-oriented experiments we were doing previously, and robot just seemed a lot safer.
Less explosive. That's good.
Well, on a good day.
How did that impact your education and your career down the road?
Yeah, I think I learned a couple things that stuck with me from that. One was just the joy of building something, having it work. And then another one was just stubbornness of you build something and it's not working. And so you just stick with it. And how do you almost celebrate problems, get curious about why it's not working instead of being give up.
It's easy to just walk away from a project that's not working and be well, that was not the best idea I've ever had. Let's move on to the next one. But sticking with it is such an important skill.
Yeah.
And then where did you end up going to college, and did you major in robotics, or what was that like for you?
Yeah, so I started undergrad in Florida State University and got a degree in mechanical engineering. But I had the fortune to work in a bunch of research labs in undergrad. So I worked in the Material Science Institute. So I was doing composite research and got to go over to the mag lab where they were testing cryogenic superconductor junctions for fusion reactors, and then later worked in a lab doing legged robotics. So we had these robots that had not just wheels, but they could get out in the real world and move around. And so starting studying nature and these kind of interesting mathematical models for how do you have legs as a robot and then build those things. And that was a lot of fun. And that's where my kind of deep work in robotics started.
It's interesting that such a natural thing for humans to walk around with legs is such a complicated robotics problem.
Yeah. Let me tell you, humans are so good at having legs. Once you look into the biological research, we sweat really well and we have legs. And that led to a lot of evolutionary fitness.
Yeah, the two defining traits of humans, legs and sweat.
Yeah.
Now, I understand you have some world records in robotics. Can you tell me a little bit about that?
Right. Yeah. So going into grad school, I started building robots. And yeah, I made little hexapedal cockroach robots and made some jumping robots, and one of each one was awarded a world record.
How did that feel? Was that I assume that's something you built towards? Like, hey, here's a record that we can go after?
No, not really. I was just being a research scientist as a grad student. I was writing papers in IEEE conferences, and it won like a best conference paper award. And I was like way more excited about that. And then
Yeah.
IEEE Spectrum picked up the coverage, and then Guinness like put the sticker on it.
Cool. So they reached out to you. I know a lot of them are more proactive on the record breakers side, but it's I think it's saying something if they come to you for something like that.
Yeah, certainly easier.
Yeah, and probably cheaper too. I've heard stories. Where did you go to grad school?
So I went to grad school at Berkeley. So coming out of undergrad, I wanted to do robotics, and in the U.S. that looked like UPenn, Carnegie Mellon, Stanford, or Berkeley. Those are the really big robotics programs. But Berkeley had this amazing program that was like collaborative between biology and engineering. And as someone that was doing liquid robotics, I was like, this is the perfect thing. Like if I get into Berkeley, I'm gonna go there and do this program over all the other schools.
That sounds fascinating. Did you get thrown in? I feel like I'd be thrown in over my head if I were trying to take grad level biology classes coming out of school with an engineering degree.
I think you'd be okay. I think grad level biology is about research, right? And this program was very thoughtfully designed and specifically designed for engineers to work with biologists. And how do you build like a research team that is better than the sum of its parts? So they had like these models and education methods of, we're going to have engineers, they're going to take some biology classes, but we're also going to have like shared seminars where biology research and engineering researchers present to each other. You develop this kind of shared base of experience while having a team of like very deep experts.
That's really fun.
Yeah, it was great. Yeah, it's something I brought to Jidex later.
What would you say your biggest surprise was going into that? And was there a moment or two where your mind was just kind of blown, like, well, there's a whole nother world that you haven't really explored here?
I was on a team doing comparative biomechanics of like, why do robots suck pretty bad as compared to animals, right? What is it about animals that's so much better? And it's just like kind of nothing, right? But their materials aren't great. They're not super fast in terms of processing power, or like there's a lot of noise in there, and just finding out that there's a system that works so well while all of its parts are just kind of like goop was fascinating to learn about. Well, they come at it with shape. That's one thing that nature masters really well, the ability to like build very detailed structures at every scale of the system. And they do so much with shape and design. And that kind of started to feel like why people got excited about 3D printing. Right? You can now easily fabricate these structures of arbitrary complexity, even though the underlying material is kind of okay. But then the overall thing is amazing.
Yeah. I don't have to have a really fancy metal mill. I can kind of just squirt some plastic on a heated platform and get any shape I want. Mm-hmm. Can you break down some of your world record setting robots for me?
Sure. So the cockroach was named Velociroach, which is kind of a portmanteau or backronym, I guess. You come up with the name first, and then you're like, the letters mean something. I forget at this point.
Going a little Jurassic Park with it, I imagine?
Yeah, it's like, it's a fast, like the original robot was Roach, and then I was like, well, it's fast, so Velociroach.
Oh, Velocity. I was thinking like Velociraptor.
But it also kind of sounds like Velociraptor.
Yeah. Fast, right?
Yeah.
In theory.
So yeah, I got to Berkeley and I was anticipating doing smart materials and robotics. That was going to be my core research area. The lab I went to had synthetic gecko adhesive, so kind of this way to make polymers, and it sticks to glass, but then it like releases like a gecko foot. And I was going to integrate those with their existing robots, and that was going to be my research. But then the existing robots it wasn't like a reliable scientific platform. It was hard to put it together in a way that behaved uniformly, and then the performance was based on like the humidity level, because they ran out of cardboard. So I was like, okay, well, I'm going to first design a platform for doing these experiments. And then that turned into my PhD. I want to be able to, run reliable experiments. And I mean, making it more repeatable, easier to put together, more rigid. And these robots were, it's about 30 grams, and it's got 6 legs and 2 motors, so 1 motor per side. And as you spin the motor, there's this cardboard mechanism that like lifts up the leg and then puts it down and takes a step and then lifts it up again. And they turned out to perform really, really well. It's another thing you learn about biology is that materials have a scale that they work really well at. And so for these 30-gram robots, cardboard is actually really, really nice to work with, and it's fast. So you can get into this space where it's very fast to design, very fast to iterate, but also customizable, and the performance is there. So it's kind of the sweet spot for a research platform.
So tell me about cardboard. I'm picturing I get a box from online distributor A, and I keep it and I cut out some shapes and have a little robot, but surely it's more complicated than that?
There's one more step. So I guess card stock is it's kind of like thick poster board.
Okay.
And then it's laminated with a flexible material that makes a joint, kind of like the lid of a Tic Tac container. It's got like that flexure joint.
Yeah.
So you can build a 3D linkage that way, just using like patterned laser cuts and a lamination cycle. So you can just go from like nothing to robot in a half hour.
Wonderful.
And this is a robot that can run like 2.7 meters per second, and you can throw it down the stairs and it still works. And yeah, it was a great little process for prototyping.
2.7 meters per second is pretty fast, especially for like a little 30-gram. I imagine like even wind resistance is a big issue at that point.
Yeah, it starts to be. And so that was the first version, was 2.7 meters per second. And then that became this kind of standard scientific platform for the lab, which I found really rewarding. Like people put shells on it, people put tails on it, people put like jumping mechanisms on it, and they were able to answer all these different scientific questions because we had done that little bit of hardware engineering to say like, here's your experimental platform. And then one question was, my advisor was like, well, how fast can it go? And he kind of kept pushing this for a while. I was super interested. It's like, okay, well, I built like a higher power version and actually had 1 motor instead of 2, so it could only like go in straight lines, and it did like aerodynamic steering instead of trying to move the legs around.
Oh, interesting. Like a fish almost, right?
Yeah, like kind of using drag or like a tail on a bird.
Huh.
And that one got up to 4.9 meters per second.
Ooh.
So that was one of the Guinness World Records. It's like extremely fast version of the robot. I think my advisor was just tickled that it was outrunning like all the cheetah robots with this like little cardboard cockroach.
Yeah, I imagine walking into the room. I'm picturing, I'm sure it didn't exist, but like robot races, and you have all these big old fancy things, and you walk in with this little cardboard contraption. I love seeing the engineering brain at work, and I'm sure that's something you brought to Jidex, which we'll get to in a little bit. First, though, it's time for a quick break. This is the only break in the whole podcast. We'll be right back. Today, I'm joined by George Harriman, a system architect at Rome, to talk electric vehicle charging. George, thanks for being here today.
Yes, hi, Daniel. It's good to be here.
So I see electric vehicle charging stations, EV charging stations popping up everywhere. Can you tell me a little bit about kind of the world of EV charging today?
Yeah, that's true. We start seeing a lot of these cars being charged. So in general, the universe of EV charging falls into 2 big categories. One is AC charging, and the other is DC charging. AC charging, there's kind of level 1, level 2, people might hear. Level 1 is the at-home type of charging. You just plug your EV car into the wall outlet, takes it from the 120 volts wall outlet, but that takes a long time to charge. And then the level 2 AC charging is, you might find them at supermarket parking lots, right? That's taken out of 240 volts charging. That's a bit faster, maybe up to 90 minutes of charging. And then the third one, which is popularly called level 3, is what is called DC fast charging. So that's where it gets more interesting, because with DC fast charging, one can charge the EV car in much faster, maybe around 20 minutes or less.
That's really fast. What is trending in the technology of DC chargers today?
Yeah, so for DC chargers, as mentioned, as the EV cars tend to have bigger batteries, in order to extend the EV car's range, DC fast charging must be able to charge the bigger batteries faster. So it has higher output power capability, and therefore it requires advanced or high performance power devices.
So what sort of devices and technologies are used inside of these chargers?
Yeah, so since we're talking about the DC fast charging, inside the DC fast charger, because it's very high output power, it's made out of this individual power supply unit or PSUs. So inside them, there are mainly two big blocks in terms of the power path itself. The first is an AC to DC conversion, which is typically done with a PFC or power factor correction block, and then it is followed by a high voltage DC to DC block. Depending on the block, various power devices from Rome can be used, such as Rome's fourth generation silicon carbide or SiC MOSFETs, SiC Schottky barrier diodes or SBD, SiC power modules, high voltage superjunction MOSFETs, insulated gate bipolar transistors or IGBT, and silicon fast recovery diodes or FRD.
So I've been hearing a lot about silicon carbide in the industry. What is it? Why is that important? And what are you doing at Rome with silicon carbide today?
Yeah. So first, I want to mention, what is silicon carbide devices for those who may not know. So silicon carbide devices is a type of wide bandgap semiconductor, and the difference compared to silicon is that it has a much higher dielectric breakdown. This allows silicon carbide devices to be made smaller, yet have lower on resistance, and still capable of operating at very high voltages. In addition, silicon carbide devices have much lower reverse recovery charge, which results in lower switching losses. Rome's fourth generation silicon carbide MOSFETs cover from 750 volts up to 1200 volts and is offered with an on resistance as low as 13 milliohm. Packages includes two types of through-hole type and one surface mount type. Rome's lineup of silicon carbide Schottky barrier diodes or SBDs range from 650 volts up to 1200 volts and are offered with rated currents from 2 amps up to 40 amps. Both through-hole and surface mount types are available.
That is a lot of current. We're out of time. Thank you, George, so much for being here.
Thank you for having me.
So we're back with Duncan. Duncan, you had another record-breaking robot, and I understand this one didn't go horizontally, but went vertically?
Yeah. So what happened was I took my little cockroach robots down to there's a FEMA disaster training site outside Menlo Park. And so there's these big broken slabs of concrete and to simulate collapsed vehicles and buildings. And I put it down next to the rubble and it was not going anywhere. The smallest rock was 3 times larger than the robot. I was like, well, this sucks.
I had a robot in high school, though. Yeah.
Yeah, robot in high school. It could have driven over it, but then this pile's 12 feet high, and I was looking at the terrain, and I was hearing first responders go through a lot. So if there's anywhere you can deploy robots, first just make sure it's stable. Set up remote monitoring really fast was something that just seemed important to be able to do. And so I found that I kind of left with this message of small robots need a better way to move in human scale environments, right? So I was like, okay, well, what do? You can climb, but then everything's really dusty when a building collapses, and it's hard to be guaranteed a great handhold or foothold. And then, or you can jump. So then I started looking at jumping systems and studying how robots worked, what had been done, how the biology, what mechanisms were there in the biology, and I found this little hole where frog legs and bush baby legs have this adaptation where if they're fully crouched, they can store a lot of energy in their tendons and then jump. So people have done the wind-up jumping robots where they wind, and then uncontrolled release. But this is a way to get a very powerful controlled release. And it's just this simple mechanism of, you drive a spring into the leg, and when it's crouched, you can just put a bunch of energy into that spring before you take off. And that became the concept for Salto, which was the jumping robot.
Okay. I'm trying to picture it. So how do you get a controlled release out of something like that? Is there just a gear mechanism, or what does that look like?
Yeah, so the actuator is something we call a series elastic actuator, where you have motor, spring, leg.
Okay.
And the leg behaves in such a way where basically the weight of the robot and the virtual force from it accelerating basically kept the leg crouched for longer, so you have longer time to wind the spring before it has this explosive release of elastic energy. And that meant you could take a 100-gram robot and give it a 4-foot standing vertical. And then it can do that again on the next jump. And then it can use that energy to jump off walls. And so you're going to have this like really hyper aggressive pogo stick robot capable of moving in extremely rough terrain because it only needs like a little point of contact where the toe touches.
And then it's probably so light, like 100 grams, that it's not really. It's pretty robust when it's landing from heights too. I imagine it can do a lot.
I always liked designing at the bottom of the size scale, and that was set by when do motors start getting really bad? So the cockroach robots use those little coreless motors, and like below 6 millimeter diameter, you can't push much flux around. And then the jumping robot needed more power, so I used a brushless motor. It's like, okay, what's the smallest brushless motor before power density, torque density starts really taking a hit? It's also safer.
I'm starting to see where having biology and engineering in the same room could become really, really useful.
Yeah.
How high did it jump? What's the record?
Not measuring the highest extent, it could jump like 4 feet standing vertical, right? So just from nothing to 4 foot high.
Do you have them on your shelf? Do you just kind of like time to time look back at them? Like, do you have the certificate on the wall and all that? Is it kind of
I've got a few little prototypes I keep on my desk of like what the old version. It used to be like only jumped in the plane, so it had this like big X-shaped foot to stabilize it before we made it able to move in 3 dimensions. So yeah, I got an old prototype there, and also the first computational structure I designed was like a little bent wire circle that the machine crashed on. So it's just just always remember that first experiment. Yeah.
Are there any moments throughout the design process of either of those where you were just pulling your hair out, and what did it take to get past that moment?
Good question. So we kind of invented some new ways to design robotic mechanisms during this process of like, it's a pretty complicated, it's like an 8-bar linkage that connects the spring, like that's the leg. And we designed it to be reactionless. And that means like you can extend it and retract it and you don't rotate at all. And your center of gravity like doesn't shift from this line that would cause you to spin. But that was banked on some assumptions of like, okay, when I design all 8 of these things and they're assembled and strong and put together, what is the mass distribution going to be? And I got that really wrong. So there was a version where it would launch and just like spin like a maniac. I was like, what is going on? And so then I had to go back and look at all my assumptions of like, okay, well, now that I have the detailed model, this is not where the mass is. I had this like mass hanging out at the knee that when it snapped through just caused the robot to spin uncontrollably. Huh. And so to get past that, we kind of updated the assumptions, updated the model parameters, went back to the mechanism design, re-optimized the whole thing.
Yeah, I think we take for granted often. I know I do. So in my free time, I do a lot of mountain biking, and the kinematics and the pivots and the suspension linkages are all really, really well refined, unless they aren't. And it becomes quickly apparent when people have done the work and when they've just kind of slapped together someone else's IP into a bike frame. Mm-hmm. And I can imagine trying to do that from the ground up would be incredibly difficult.
It was a good challenge. I was really trying to draw a lot on design tools and maybe build some new design tools to help with that process, because it's kind of an ambitious goal of like getting something like that energetic. I think it pulls like 14 Gs in when it lands. Like it's a lot of acceleration.
That's insane. Yeah, that's a lot. My goodness. A lot. Okay. Did you ever have moments where it just like exploded all over the lab and you're trying to find parts?
Lots of robot pieces. Yeah. Yeah. And like legged roboticists tend to do this. Like we have carts of like burnt out motors and like overvolted batteries. And like we're just trying to juice as much performance out of this thing as possible. And yeah, there's a lot of vacuuming sessions, I guess. Just like pick up all the shreds of carbon fiber and all the little carefully designed pieces.
Yeah, I stepped on a dip package the other day in my lab barefoot, and it was not good. I can imagine.
Ultra Lego. Yeah, that sucks.
It's worse than a Lego, let me tell you.
Yeah.
And then out of school, how did you shift over to Jidex? And then can you tell me about that transition from robots to software?
So I met one of my future co-founders when he came by our robotics lab looking to use our pick and place machine. So he had a project called Chisel, where they basically took the idea of programming language design and said, let's do it for digital logic design, right? And this became like a really big thing, spun out a bunch of companies and labs that Intel is funding. And he wanted to use it to build like a discrete, kind of like a vintage computer compiler. because you could take this high level logic and then compile it to like 74 series logic. And you want to use a pick and place to like generate these little computer boards.
How fun.
It's like, well, that's just a cool thing to do. I want to know, I want to get to know this guy.
Right.
And then he taught a class in the architecture department where they were looking at computational design. So I went over there and I was kind of learning these ideas, and I saw how when you have this approach, so his style is you take code and you use it to represent like a hardware engineering process, like this pipeline of ideas where you go from like high level concept through successive iteration all the way through to like the manufacturing files, right? So like you go high level to like, I'm making this thing without touching it. And just seeing that transformative aspect was so cool, like seeing what it could do for hardware design. And I was coupling this back to like, okay, I designed this experimental platform. What if everybody could do that? What if everybody could just design whatever they want? And once they did, it's like this reusable thing instead of this one-off artifact. Yeah, we got really, really excited about this idea. Took the class, made my folded robot design tool where you put in like, what are your linkage dimensions? And it'll spit out like those laser cutter files, ready to go. And then he was presenting Chisel at Sketching and Hardware, and the creator of the Beagle Bone. Are you familiar with that board?
He was actually on this podcast, episode 19, but keep going.
So he was there, like, thought about doing this for boards. Like, boards are terrible to design. It's really, really hard. And so then he came back and he talked to me. It's like, what about the circuit boards? I was like, yes, that's really, really difficult. Right? So like one of the things, like the jumping robot had to have everything custom, like materials, mechanisms, motors, drivers, as well as electronics. And like the electronics took a good chunk of time to figure out, okay, like what motor topology do we need, and like what can we fit where, and what's the battery look like, and just took a long time to iterate. And there was like one guy in our lab that could do PCB design.
Yeah.
And I thought back to undergrad, I was like, well, there's nobody there that could do PCB design. And then we talked to our grant partners. So they were tagged up with Chisel to basically make the design of SOCs 10 times more productive. So we talked to Northrop Grumman, this team that can buy all the licenses, all the equipment that they want. And they're also strapped from their design tools, right? All the money they could buy, and they still don't have enough correctness and productivity. And it's like, okay, maybe there's like an opportunity here to do it for circuit boards. And then, we kept talking to people and then spun out of Berkeley around August 2017.
So it sounds like the dream is essentially, I want a board that can do this, have this functionality. And they say, okay, here are your Gerber files.
I think the motivation is, how do you take the best of how we as a species know how to design hardware and apply it to every single design? How do you make like the world's most expert knowledge like reusable, repeatable, scalable, kind of in the way that software is, right? Very few full stack programmers have to like re-implement the Linux kernel, for example.
Right. Yeah.
Right.
Let's hope not. Yeah.
Right. You have like all this really, really high performance automation. How do you bring that to the rest of hardware design? And that was the idea behind Jidex.
So what is Jidex and how does it work?
So Jidex is a way for us hardware engineers to write code to design electronics. So think about how it works. In a traditional CAD tool, let's add a part to the design. You like go to your library and you like drag in a symbol for, let's say an LDO. Now you've got a symbol on the schematic sheet and you can get a land pattern to show up on the board. And under the hood, the CAD model has, that CAD tool has a model of the component. Like, oh, here's the shape of the symbol, and then here's like the shape of all the pads. And so some user went in and drew those. So when you add it to your design, the CAD tool is like, all right, I'm going to add these shapes to the design with some smarts. So it knows like, when I draw a wire to this location on the symbol, it means I'm trying to make a netlist. And in Jidex, the flow is similar. So I would write a line of code saying, instantiate something called AVDD regulator to my design, which is this analog devices component. And when I run that line of code in Jidex, it produces a schematic and it produces a board. So we're kind of back to what we had before. And I could actually take that Jidex design and export it to an existing CAD tool and like do whatever I want there.
Interesting. So basically instead of doing the whole GUI, run around to get everything set up, you can kind of just type in a couple lines of code and it will set it up for you. Is that what I'm hearing?
Yeah, yeah, and so like it's not we don't want to just like make a new way. We want to get like design superpowers, right?
Yeah.
So that component model in JITX is code. Yeah, it's pretty simple code. Like here's my list of pins. Here are the pads that they map to. Uh, and there's like a pointer to the land pattern of which is usually like a parametric call, like make a little SOIC package with this thermal pad dimension and 8 pins. So yeah, so the component model has become code, right? And so my line of design code can have parameters now. So instead of having just a single part, I could say, okay, this component has a parameter called output voltage, and I could maybe model that entire family of voltage regulators. My line of code would now say like instantiate AVD regulator, which is a 2.5 volt version of this LDO. So you start getting a bit more power that way. And we tend to kind of create a lot of those parametric part families. You have parametric capacitors of like, I need a capacitor with that's like X7R and has this voltage rating and this capacitance, or microcontrollers. Right? I need an STM32F4 that's, well, just in stock, and I'll start there.
Yeah.
So you kind of get that parametric way to start interacting with your part library and your supply chain.
Awesome.
Yeah, it's just a bit more productive. And then I think the final part in JITX is that you also get subcircuits. Right. So when I'm doing this LDO, I'm reading the data sheet. So I'm going to say, okay, it needs this capacitor, it needs this set of things. I need to like put in this design equation to calculate the feedback resistors, or here's like a gotcha, like, oh, I need a cap on this exact pin if it's going to work in this way. And so then you can start adding circuits programmatically. And then the thing that gets all that sort of magic stuff to work is you add checks to it as well. And this is a set of analyses that run every time you use that LDO circuit in a design. So like, what do you need to know to make sure that's actually going to produce this output voltage? Like it's stable with this capacitance and the ESR of this capacitor, and the input voltage is provided correctly. And so when you run that, you get your circuit out, which has like all these parametric parts that you added, but you also get this kind of verification report of like all your schematic review stuff, all the little gotchas that maybe you're used to like making notes off to the side of when someone adds this component to a design, like check this one issue from the silicon errata. You just kind of get to bake all that into your code.
Fascinating. So essentially a lot of the gotchas that you might miss while having to read through data sheets or trying to remember, 30 or 50 or 100 data sheets, it's all baked into JITX and will run some of those checks for you to make sure you're not making any mistakes.
Yeah, exactly. And then you can kind of start putting your design together out of these circuit blocks. And each one you've baked enough knowledge in to know that it's going to work. Right. And that's where you start getting really, really powerful reuse.
Keeping in mind that our listeners are pretty tech savvy, pretty electronic savvy, can you walk me through another project and what that workflow looks like?
Yeah. And maybe I'll pick on one of my own projects here. So I've got a project I want to be designing a PCB mounted force sensor. So it's not going to be super accurate or super like high load, but it is going to be fast. And so you can do that by basically taking 4 photodiode kind of emitter detector pairs and putting them underneath a 10 by 10 millimeter block of rubber. So you kind of press on the rubber and then you detect the distance, right? So if you press down, everything reads like, oh, this got closer. If you press forward, then you see a differential signal.
So like the thinner it is, the brighter it is, and then you get an analog.
Yeah, it's basically using those little, the emitter detector pairs that your cell phone uses, like how close to an ear am I?
Yeah.
That component, and you just put 4 of those under a chunk of rubber, and you can figure out how the rubber is wiggling.
Perfect.
Yeah. So for that, I'll choose a component. I'll just go find this sensor that I want to use, or maybe a couple that I want to evaluate. And then I'd probably make my sensor module. So I define a subcircuit and put down 4 of these sensors in an array. I make some logical ports there. So I know like, here are my drive signals, here are my analog sense signals. And I would be adding some electrical properties to the sensor of like, okay, what's the responsivity of the photodiode? What are the characteristics of the LED brightness versus current, right?
Yeah.
And then, so that's my little sensor module. I'll pop that down in the design. And on the other side, I've got a microcontroller. And I'll say, there's one line of code that says like, add a microcontroller to my design. Then I give it some parameters, right? Give me STM32F0. Like, this can be a small design. Make it in stock, right? I don't need many, but here are my distributors. Go find one that's in stock and make sure you can solve this pin assignment problem, which is just these 4 ADC signals, maybe some other serial devices if I want to put on the board.
Sorry to interrupt. You're defining all this in the Jidex software?
Yeah.
Okay.
So basically, we have this parametric microcontroller, and you can pass it whatever arguments you want to set it up, like what are the series requirements, how do you want to do your clocking, how do you want to do your debug, and those just become arguments that drive circuit generators that say like, all right, here's your microcontroller, here's the clocks, reset, debug, solve the I/O for you as well. And you can wrap that whole thing in a big solver. And we modeled like all STM32 microcontrollers because they just release all the data on them. So now I have this database where I can actually query which ones are in stock and automatically design in the one that fits all my design requirements.
Yeah.
So now we got microcontroller over here, and we got sensors over here. And then I have I'm sure I've got a transimpedance amplifier circuit kicking around somewhere. But I'd say like, okay, based on my ADC parameters and the characteristics of the sensor, create this transimpedance amplifier on these input signals, connect the inputs to the sensor, outputs to the microcontroller, and set the gain appropriately. And I can do that parametrically based on how the ADC is set up. And then the nice thing is like, you just verify this entire system. So you start running checks on it. And the checks do things like set up, okay, is everything powered correctly? Am I overdriving anything? Have my capacitors and resistors been derated appropriately for reliability? Are my signal parameters going to be respected? And so you get this like the schematic, the board, but also this very, very detailed verification report.
Normally I'd have, 5 monitors with 30 data sheets, and I'd be trying to like cross-correlate all the pins to make sure everything's correct. Right? But you're saying with Jidex, it essentially does that for you and does some like design rule checking? Yeah,
so pretty detailed design rule checking. We had some learnings and found that it's actually really important to treat verification as like a first-class thing in the language. So when you model sensors or you create a power regulator circuit, you can add a check to it that says like, when this is added to any design, you need to respect all of these things, like all the little gotchas in the datasheet, all the parameters. You're not sure how it's going to affect something else later, but the model is you read a datasheet once, you encode everything that matters about how you're going to design the circuit in, and then that checking is automated for you. What it feels like as a designer is like you're kind of working at the system level, and all of the kind of serialized concerns of making footprints or drafting a schematic or running a verification or doing layout, they'll all kind of stack into one, where you're like iterating on your code, and it's running the checks for you, and it's running component sourcing for you, so you actually know exactly what you're working on and where the problems are. So you can change around at the high level. Oh, I need a different microcontroller, or I need a different op-amp for this transimpedance amplifier, or I need to power this thing differently, or I had anticipated these power demands. And all the lessons learned, that you have as a hardware designer, you get to bake those in. So you don't have to worry about, did I remember that special checklist item that makes this component work?
Yeah, I remember reading into, I forget what the chip was, but it was a power, it was like a DC to DC converter, and reading through the woes of people trying to get that chip working properly was interesting. I ended up going with a different chip just because I didn't want to have to be one of those people in the forum threads trying to get that thing working. So I imagine having some of that baked in and programmatically decided, especially in 2020 and beyond, when trying to, it seems like bombs are changing constantly.
Yeah. And the ability to change a bomb constantly is like a sustainable competitive advantage.
Yeah.
So that's one thing the checking gets you is like, can I swap these parts? Right. And if you do it enough, you can say like, well, I can swap out any microcontroller into this design and I know it's going to work. And then you get to optimize over that.
That's pretty magical.
Yeah. And it feels kind of magical, but it's just automating model-based engineering, like the checks that we usually do that are sometimes baked off in a spreadsheet or just like sketched out somewhere. This would just become like a native part of your design tool. It should feel like as you design, things just get faster, right? Because I'm trying to get that feeling back of like when you're doing this code is you're not doing a design, you're automating your design process. So then you can change parameters and then new designs just come out of this thing that you're building.
Do you have, is this where you plan to start out with Jidex? Like, was that the end goal, or what was kind of the vision from the start versus where you are now? It's been, what, 5 years?
Yeah. So the goal was always, how do you make that expert level hardware engineering like more reusable, more impactful, right? Really, really scale it out. And then the business model has always been kind of flexible. So at first we participated in a DARPA contract and like developed like as part of this open source initiative, the ERI. And we also were operating as a design consultancy. So we were dogfooding our own design tool, like taking on real customers, real designs, doing them ourselves, noticing what didn't work and what was really bad. And we did that until the technology got good enough. Because like we're making a tool for experts and it has to like meaningfully help them very quickly or it's not worth anything at all. Right. So that's like a really high viable bar for minimum viable product.
Yeah.
So we did that for a couple of years until the language stabilized. It was solving the right problems. You know, we guessed the technology wrong to start with. Like we built this thing where you can create a prototype very, very quickly. You know, it's 100% automated. Say like, here's your sensors, microcontroller, and create a board. And no one cared because it wasn't valuable. It's a good prototyping tool, but turns out prototypes are not the most valuable thing to optimize for.
What is?
I think it's the work of these senior engineers, and large of it scales more towards verification, right? How do you make sure that designs are correct? Because that's been the big push, especially with the component shortage, where components can be extremely precious. And you have companies saying, like, we don't make coasters here. Like, we don't have any bad boards. So that verification aspect was really important to get right. And another thing that changed was this system focus, right? Where you need to say, like, things like, based on the routed length of this line, if it exceeds 5 times the rise time of the signal, then you need to add this termination resistor. And our approach had been kind of similar to digital logic chips up to that point, where you have this like script-driven pipeline where it goes from like high level to low level. That doesn't work for electronics. You have all these like kind of cyclical dependencies. So getting that in and getting it working with verification was the big unlocker for making it valuable.
Yeah. That was one of my questions when I was reading up on this is what sort of bandwidths or like speeds, rise times, where does this where's your practical limit now and where do you hope to get with that in the long run?
Yeah, good question. So we actually don't have any limits on that because we are focused at the schematic level right now. And, the signal integrity is largely about shapes, right?
Yeah.
And we're looking at designing you can do extremely large designs, like 100 B-size schematic sheets, and it comes out correct because software is pretty good at doing that. Cool. But it doesn't touch the geometry in a significant way yet, but that's actually coming next. So we're getting full design back, but actually making it really optimized. Like, how do you design this? How do you select a processor that's in stock and also routable for your system in the fewest number of layers? Yeah, like, that's an interesting question, right? So now we're bringing automation to answer things like that.
Yeah, so right now you said CAD files, so you're getting to like a KiCad or Altium type file. Is that correct?
Yeah, that's right. Yeah, talking to Cadence and Mentor Graphics as well. We just import and export for those tools. So we're that flow from requirements to design generation to design checking, and then it goes right back into the existing flow.
What has surprised you the most as you started working with expert level PCB designers?
I think the data problems were the most surprising. Like from the outside, and I think this is still true, like if you send like a well-constructed zip file to a factory, they can probably send you hardware back. But then actually the standards for saying like what information is needed, what does it actually mean? Did you mean to do this? As well as on the component side, the lack of good models, good data sets for components. That was a bit of a surprise. The fact that most manufacturer-provided SPICE models are not useful and useful for design creation, design checking. If you talk to them, you can get like a purpose-built model if you're big enough. But then given all the economic leverage in the world, it's still not fixed. Like, this is a massive industry to have this kind of uncertainty about how to even represent data to start using it programmatically.
And this is where it feels like there's so much knowledge gained from experience and from failing and being okay to fail and learning from it.
It is. Yeah. And that was the dream of like, how do you make that lesson learned reusable, right? How do you like make it so when you publish a design, if you choose to share it, it's not just the design, but if someone wanted to customize it, they could basically take everything you learned about how this went together and meaningfully reuse it.
So if I were to go on and use this tool and say, I have a custom chip that we fabricated for this design, how do we go about importing a custom chip? And is that even an option?
Yeah, of course. So models for components are just code. The typical model looks a lot like that pin table you see in the datasheet. And then it's slightly rearranged, and then it'll do pin assignment as well as like symbol creation if you want. That's the most typical one, is just like, here are my IO banks, just generate a set of box symbols for this chip. So it's just like a little piece of script you include in your design.
Okay. Doable sounding.
Oh, yeah. Yeah. And if you have like a larger set of components, you can also like scrape all of these parameters and put them into a database and then optimize across the set of chips. So just kind of when we do import, we also do a lot of kind of design merging, right? So merge like the land pattern generators from STM32 with all of the like IO capabilities, right? So try to create one representation out of little pockets of data that you find here and there.
Yeah, this is fascinating stuff. What has been the response when you show this to people? And what's people's first general response? And then what's been the response of people who have gotten their hands on it and really gotten to work with it?
Yeah. So initial response, you kind of see breaking down into two camps of one's like, I've been doing this for 20 years. I'm never going to write a line of code in my life. Like I've got my off-ramp to retirement set.
That's why I got into this, so I didn't have to write code. Yeah.
Yeah. And the other one is like, I've been doing this for 20 years. Where have you been? Like I tried building this myself 5 years ago, and they'll show you the cathedral of a spreadsheet they used to like design a backplane net list. And so those are pretty consistently the ones. So like, of course, this is a good idea. And then there's no way. And then what follows that is usually like, how could this possibly work? And those are our initial reactions. Yeah.
Now, honestly, if I'm being honest, that was my first impression, is like I said, it sounds too good to be true, because I've spent so many hours pouring through data sheets and forums and trying to just figure out what's going on.
Yeah.
For me feels not right.
We worked really, really hard on it, and we talked to a lot of smart people. It's really not easy. And this idea of making better design tools is not new. I think everyone kind of notices like, hey, a lot of electrical engineers have a bit of angst about their design tools. But I think we're the first ones to take this kind of productivity-oriented approach to it, right? How do you make a language that really makes hardware engineering take off?
Can you talk a little bit about the design tool environment at large? And again, coming in with fresh eyes, what was your take on just how everything played together in general? Because I know I have so many different EXEs on my hard drive.
So what I saw is like there's actually a lot of good small pockets of automation, right? There's like little circuit calculators, and there's little antenna optimizers, and there's like these little domains of automation, but there's nothing connecting them besides human brains, right? And that's kind of what you see as a design team as well, is like, okay, well, we've got to design this clock distribution tree, and like, okay, here's our big spreadsheet for doing phase noise analysis. And it's piped through a human brain that reads, data sheets, puts numbers in spreadsheets. And in this space for tooling, there's nothing. Like the most common wisdom you have as a startup is like your competition is Microsoft Excel. And that's also true for design tools, right? And then downstream, there's like a lot of existing tools for once you know what you want to do, then you can draw a schematic. I think the layout tools are pretty good for humans kind of pushing shapes around. Like that seems like a well-defined interface. I think there are good auto-routers, although that's a contentious belief, I know.
You might start some wars with that hot take.
Well, I'll say that the algorithm is fine for what it does, but you do have to box it in, right? You have to say, like, here are all of your geometric constraints and write only these signals in this little part of the board. And if you use one of the top end auto routers, it does work. But people, of course, argue that that's not a productive way to do things.
You alluded that you're maybe working on more of a layout type tool too. Can you tell us?
Yeah, absolutely. So you notice that like auto routers are okay at what they do, but driving them is kind of painful. So our approach is like we actually know all of the smarts about the system, its electrical characteristics, how it's supposed to function, like what are the eye diagrams of these receivers and what are the transmitters and the material properties for everything on the board. So being able to drive all of that high level intelligence down to like creating geometry and then evaluating it as well. So extending the automation to get more design happening inside the tool and then also checking that as well. So you get the schematic and layout checks of, is the parasitic capacitance on this bus too high? And then not having to open any data sheets to get that answer is is what's coming next.
And then where do you see the PCB industry going overall in the next, 5, 10, 15 years?
Yeah, I mean, it'll be an interesting time. I think geopolitically, we have a lot of senators going to fab sites now and getting their pictures taken. That's new. On the technical side, I think it'd still be the media of integration, right? There'll be more complex chips. Something we're doing recently is like also extending into advanced packaging, and it's kind of like an extension of PCB design. And so I think it'll still be this thermal is going to be really important. I think you're going to get more sensitive radios placed next to more things. So it's still going to be that interesting space where a bunch of hardware disciplines are merging.
Yeah. Do you have any advice for students or entry or even intermediate level career folks who are wanting to get better at PCB design? Anything that they should start doing or stop doing or places they should go to learn more?
You got to be careful with advice because everyone's so specific in what they're trying to do. I think just build things, right? Build things, be curious about why it worked, be curious about why it didn't work, and just keep going.
I'm definitely a learn by failing sort of person, so I like that a lot. Any advice for folks getting started in the world of startups or any surprises going from like a research role into a startup role?
Yeah. So, and by startup, do you mean like a venture-backed startup? Like you're going to go, all right, so your market's like valued in the billions because that's what investors like to see. And you're going to go raise some capital from venture capitalists. So for that startup consideration, like your listeners are like hardware people. They know how to build hard things. They know how to focus on things that are valuable. And that part is going to be so specific to what they're doing that it's hard to give any advice on. So I guess the first point is like, watch out for a lot of the startup advice you find on the internet. People give it very freely as a way to like establish their reputations or as like content marketing for their VC firm. And then I think the second point is like investors are driven by FOMO, right? Fear of missing out. They don't want to be that person that passed on like Stripe or Airbnb, right?
Sure.
And to drive that FOMO, you just have to explain what you're doing really, really well. And the easiest way to explain it to investors is like make money, right? So just make like a real business, try to make real money right away. And then you can explain it as easily as possible and start creating that sort of lots and lots of interest around what you're doing. Just like build something valuable and then explain it was, I think, Paul Graham's YC advice.
Wonderful.
Yeah. And I guess if you're just starting out, there's investors that have a didactic focus, like Y Combinator, and also Sequoia has early programs. So we benefited a lot from there. And if anyone wants an intro, please reach out. You can just send me an email. Happy to make introductions.
That's very generous. I'm sure a couple folks will take you up on that. It's an interesting world to explore, especially how did it feel coming out of like a research space into like VC startup world?
I think you just get more audiences, I guess. So like in research, you focus on the research and your audience are your peers, right? Technical people that are interested in the technical matter that you're doing. And then big change to the startup is now you have to explain like to investors what you're doing. You have to explain to customers what you're doing. You have to explain to people that you're trying to recruit what you're doing. So you kind of end up just creating a bunch of different lenses for the same thing. So that's a big thing that changed. But Jidex is like our software is really hard to build and we're constantly solving new problems. So a lot of it does have that same sort of research flavor.
So what is next? What are you building next for Jidex? Where do you see the industry overall in 5, 10, 15, or even like 50 years?
Yeah. So, what's next for JITX? We are building out those libraries. So, working with semiconductor vendors to say, like, okay, you're making application designs right now. What if you just like have some code and you can generate every application design, and then you can like piece them together into complete systems. So it kind of helped get the data populated out. It's because if anyone's going to bake in expert knowledge about a part, why not have the semiconductor people do it? We're building full design automation, so you can actually start doing, like, have interesting control over like place and route algorithms inside JITX, and then take all those electrical checks I mentioned and extend them to physical checks of, the total capacitance on this bus is not going to interfere with the electrical functionality of the part. And then we're also getting into advanced packaging. So, the folks are moving towards chiplets, and now you need to chop up your die into like a bunch of little pieces. And it turns out that creates all of the problems that we solved at the circuit board level. So now we're helping people design systems of chiplets on interposers, on packages, on boards. And it turns out you can do that all from inside JITX and not have like those, when like you kind of put a boundary in a design process and like, oh, this team's going to design the board or this team's going to design the package. Then you have like a bunch of errors. When you dissolve that, it actually system design gets really, really nice.
So what does the future of this space look like? I know it's one that's been a little sensitive to change, and things like personal computing power have dramatically overhauled it. Is this another stage of like a change in the industry?
Yeah, so I see progression of future trends, like things will keep getting tighter and denser and faster. And so things that used to be separate, like thermal simulation and power simulation and like signal integrity simulation, are gonna kind of merge into one thing, and you're starting to see some of that coming up at DesignCon, right? PCBs will still be the method of interconnection. You're going to have new fabrication processes to target, like I think IMSAP, things like that will start being more common, and you'll also see probably more diversification, right? So silicon is changing a lot, and they've actually had decent automation tools, but now they're really ramping it up. So you're going to see like mass customized silicon to applications, but then the board is still going to be this like place where you have to integrate everything and put sensitive radios next to new kinds of processors and get them to work.
Yeah.
Right.
Yeah. It's not getting more simple, that's for sure.
No.
Well, we're wrapping up on time. At the end of every podcast, we like to do a lightning round where we ask a couple quick, some off the cuff, some, a little more casual questions. In your study of the animal kingdom, are there any animals that you wish you could have explored the kinematics of a little more?
Mm-hmm. Yeah, I would have loved to explore flight. We were running some jumping studies at Berkeley, and mostly with their extremely fat squirrels on campus.
Very Mark Rober of you.
Yeah. We had one Stellar Jay hop onto the course, and it was doing these flips back and forth between branches using its wings to flip itself around in midair. Such a cool capability.
Yeah. Maybe if in a different world you could have built the first like human wing set or something. Who knows? In the world of pop culture, are there any books, movies, TV shows that really get robotics right, and any that really get it wrong?
Oh, I think there's plenty that get it wrong. I liked the Red Mars trilogy, and their idea of what robots should be doing for a society. Not necessarily the technical functionality, but like, what should we be using robots for? How should they actually have positive benefit for what we're doing as a species?
I'll definitely put that one on the reading list. Thank you. And thanks for being here today. This was awesome.
Yeah, thanks for having me. This was really, really cool. I've been listening to the podcast for, well, I guess since we first talked. It's really good. I had no idea. Yeah.
Well, thank you. It is definitely a team effort. Shout out to the EE Tech Media Group and All About Circuits team for making this happen. We don't do credits on this podcast. I kind of think we should, and they're going to tell me to cut this, but I won't because they deserve some credit, and this podcast wouldn't happen without them. So shout out to Dale and Tara and that whole team. That's it for our show today. That was Duncan Haldane, CEO and co-founder of JITX. Thank you for joining me today in the lobby. This was also the last episode of Season 5, and we're already working on Season 6. We have folks lined up from Intel and Synopsys. It's going to be awesome, so sit tight and we'll be right back. Also, if you like this podcast, go tag someone on a Moore's Lobby social media post, and if you live in the USA or Canada, we will send you some swag. We'd also love to hear who you would like to have on this podcast, so go put it in the comments or reach out if you have some suggestions for us. And hey, since we have a little bit of time, go check out some of the past episodes that you haven't heard yet. For example, Skywater and Argo AI were a couple popular ones on YouTube. Those are some great episodes, but there's a bunch more, so just go check them out. And if you haven't listened to them, honestly, I do feel like they're all worth listening to. And that's probably enough of me talking. Thank you for joining me today in the lobby. I'm Daniel Bogdanoff, and I will see you in Season 6.